Okay, in this video we are going to finish up Chapter 1, Section 7, dealing with linear equalities in one variable. And today our big idea is going to be these ones with absolute values in them. Okay, first some stuff from the book. And we got here inequalities involving absolute values. And in the setup here it says, let x be a variable or an algebraic expression, and let a be a real number such that a is greater than or equal to 0. And that's just saying this number a has to be a positive number. And now we got two cases here. The first one, the solutions of the absolute value of x is less than a are all the values of x that lie between negative a and positive a. In other words, the absolute value of x is less than a if and only if negative a is less than x is less than a. And we can think about it this way. If we have the absolute value of x is less than some number, let's say 4. If I want to get rid of the absolute value bars, remember the bars are important. They do a job and they make whatever in the bars into a positive number. So only positive things come out. But before the bars do their job, what's in here might be negative, and then the bars do their job and what comes out is positive. So if we want to get rid of those bars, what we're going to do here is copy the inequality on this side. That will also be a less than sign. And I'm going to bring the number over here, and over here it's a positive 4. On the left, I'm going to make it a negative 4. And now we can drop the bars. Negative 4 is less than x, which is less than 4. We've turned it into a double inequality. We've dropped the bars to account for negative possibilities inside of there. And I'm real big on the graphs of these, so let's do a quick graph here. And we just got to keep it, bare bones. We don't need all the numbers in between negative 4 and 4, but we know at negative 4 and 4 we got some important stuff happening. And to graph these doubles, I first like to look at this piece. My variable's on the left, and I know x is less than 4. So at 4, I'm going to have a parenthesis, and my arrow will be going to the left. And then I can concentrate in on this piece. Negative 4 is less than x, or I could rewrite it as x is greater than negative 4. So I'm here at negative 4, and I'm going greater than that, so I'm headed to the right. So here are all the solutions to our original inequality. The absolute value of x is less than 4. If I pick a number in here like 3, I can plug 3 in. 3 is less than 4. If I plug in negative 3, the bars would do their job and take care of the negative, and that would be 3 is less than 4. And those are all true solutions, so those are solutions to our inequality. If I go outside of this interval, say to 5, or down here to negative 6, and plug those in, I'm going to get false statements. If I plug in the negative 6, I get negative 6 is less than 4. The bars turn the negative 6 to a positive, and I got 6 is less than 4, which is not true. In between 4 and negative 4 are where all the solutions will lie. And let me back that up. That was for the less than symbol. We started originally, back up. We started here with absolute value of x is less than 4. What if that was greater than? Well, that's our scenario 2 here. The solutions of the absolute value of x is greater than a are all the values of x that are less than negative a or greater than a. Or the absolute value of x is greater than a if and only if x is less than negative a or x is greater than positive a. This is our compound inequalities. It's two inequalities with an or in there. We could also do this one as a double. Now let's check what that's going to look like. The absolute value of x is greater than, let me pick, let's say 6 this time. All right, same song and dance. I'm going to copy my inequality over here. This 6 is going to get mirrored over and become its negative counterpart. Negative 6 is greater than x is greater than 6. Again, we drop the bars because we accounted for the negative possibilities that occur within the absolute value bars. So if I were to sketch a number line here, I know something's going on at 6, something's going on at negative 6, 0's in the middle. If I just focus in on this part, x is greater than 6. So I'm going to have a parenthesis at 6, and greater than means I'm headed off to the right. This other part here negative 6 is greater than x. You know, we could write that backwards if we flip the inequality. X is less than negative 6. So if I'm at negative 6, I'm headed off to the left, less than. And now if we think about, testing some of these intervals out, if I pick any number in between here, say 2 or negative 2, both of those would have the same absolute value of positive 2. Is 2 greater than 6? No. So all these in here are not solutions. But if I pick any number above 6, say 7 or 10, and I plug it in, the absolute value of 10 is 10, and that is greater than 6. The same thing will occur here to the left of negative 6. No matter what number I pick, like negative 12, these absolute value bars will do their job, and that will turn into a positive 12, and 12 is greater than 6. Okay, let's try some examples out here. And I think for this section, this is our only example with 3 parts here. Solve each inequality. And we're also going to do a quick sketch of the graph just because I'm such a math nerd. I love graphing these inequalities. Let me move these down here. All right, the absolute value of x minus 5 is less than 2. All right, let's get rid of the bars. To drop the bars, we'll copy the inequality and reflect that 2 to the other side and make it negative 2. Is less than x minus 5 is less than 2. Now this turns into a problem sort of like we were dealing with in the last lesson. Want to get x alone in the middle, so I'm going to add 5 in the middle, and to be fair, I'm going to add it to the left and the right. So let's see what we have now. Negative 2 and 5, that adds up to 3, is less than x, is less than 5 plus 2 is 7. So let's do a little graph of that. Why not? Again, I'm only interested in these points, 3 and 7. And if I look here on the right, x is less than 7. So that means parenthesis at 7, and I'm headed to the left. And then I have this part that says 3 is less than x, or x is greater than 3. So if I'm at 3, I'm going to be heading to the right. And let me just copy the original inequality here. So if I pick any number in between 3 and 7, say 5. If I plug 5 in, I'll get 5 minus 5 is 0, and the bars do nothing because 0 is neither positive nor negative. And 0 is less than true, or less than 2, so that is a true solution. So all the numbers between 3 and 7 are going to be good. But if I stray outside the interval, say to 2, and I plug a 2 in there, 2 minus 5 is negative 3, and the absolute value of that will make it positive 3. Is 3 less than 2? No. So out here, outside the interval, we get false statements in our original inequality. Same thing will happen over here. Say if I plug in a 9. 9 minus 5 is 4. The absolute value of 4 is 4. And 4 is not less than 2. So again, out here we will get false statements in our original inequality. The solutions lie between 3 and 7. Ooh, and this is a good one too. Let's plug in an endpoint. What if I plug 3 exactly in? Then I get the absolute value of 3 minus 5 is less than 2. 3 minus 5 is negative 2. The bars do their job. It turns the negative 2 into a positive. Is 2 less than 2? No, not at all. So here the endpoints are not part of the solution. If, on the other hand, this was a less than or equal to sign, would it now be true? Yes, 2 is equal to 2, and our graph would be slightly different. If that was the case, we would have brackets here instead of parentheses. Remember, brackets means that endpoint is part of the solution set. All right, letter B. Pretty similar to letter A if we look at them side by side. The only thing different here, we got a little something different going on in the bars, but now it's a greater than sign, and this is greater than or equal to. So let's try this one out. Copy the inequality and reflect the 7 to the negative on the other side. Negative 7 is greater than or equal to x plus 3. The bars are no longer necessary. Greater than positive 7. To get x in the middle alone, we subtract 3 all the way around. Negative 7 and negative 3 are negative 10, which is greater than or equal to x, which is greater than or equal to 4 or 7 minus 3 is 4. So to look at the number line, we're going to be here at negative 10, Here would be 4. I usually like to point out 0 on there. X is greater than or equal to 4. So the or equal to means there will be a bracket, not a parenthesis, and we're headed off to the right. And this part says negative 10 is greater than or equal to x, or x is less than or equal to negative 10. So here's one where we have the arrows going in opposite directions. I don't like that arrow. There we go. And if we want to check some answers, here in our original inequality, any number between 4 and negative 10 is going to give us a false answer. Like if I plug in negative 2. Negative 2 plus 3 is positive 1. The bars leave it as positive 1. Is 1 greater than 7? No. So in here, we do not have solutions. If we go greater than 4 or less than negative 10 and plug any of those numbers in here, we're going to get a true statement. And this is a good one, too, to point out the exact endpoints. Let's say I plug 4 into the original inequality. The absolute value of 4 plus 3, is that greater than or equal to 7? Well, 4 plus 3 is 7. The bars would leave it as a positive 7. Is 7 greater than 7? No, but we do have the or equal to part. Is 7 equal to 7? Yes. So here the endpoints are part of the solution set. Now we have to be a little more careful with the last one here. Notice when we compare it to A and B, in A and B the absolute value bars were all by themselves. They were isolated to the left of our inequality. Here we got something else going on. We got this times 2 out front. So that is the first thing we want to address. And there's two ways we can do that. We can either distribute the 2 in the bars and then do everything just like we did in part A or B, or another way to get these absolute value bars alone would be to divide both sides by 2 to get started. If you do distribute, you will get the right answer. It'll take you a couple more steps, and in every step there's a chance to make another mistake. Over the years I've seen students distribute the 2 to the x and have 2x plus 10. They forgot to distribute the 2 to the 10, and that little mistake will echo through the rest of the problem and give you the incorrect answer. So I'm going to try to keep it short and simple. I'm going to divide by 2. So now those are gone, and I have my x plus 10 in bars greater than or equal to 9 halves. Now that I got the absolute value bars alone, I can, put my negative 9 halves on the other side. So negative 9 halves is greater than or equal to x plus 10 is greater than or equal to positive 9 halves. Okay, we want to get that x alone in the middle. So, of course, we are going to subtract 10. And another way to think of 10, since we got halves on either side, 9 halves, 10 is 20 halves. So if I subtract 20 halves from each side, negative 9 halves minus 20 more halves will be negative 29 halves. Greater than or equal to x, greater than or equal to. Now here I'm subtracting 20 halves. 9 minus 20 is negative 11 halves. If you wrote them as decimals, decimals are acceptable. We could have wrote this as negative 4.5. And if we subtract 10 from an already negative 4.5, we'd get negative 14 and a half. Greater than or equal to x, greater than or equal to. This would be 4.5 minus 10, which would take us to negative 5.5. And just a real quick graph. Let's see here. Now these are both negative, so be careful. This is another reason why I like to point out 0 most of the time when I'm graphing these. If this is 0, negative 11 halves might be about here, and negative 29 halves would be to the left of that. So greater than or equal to negative 11 halves means we're headed to the right from negative 11 halves, heading towards 0. Negative 14.5 is greater than or equal to x, means we're going to be here at negative 29 halves, headed to the left. There we go. Okay, time for some practice for you. I think there's 4. Oh, no, let's back up here a little bit. This is an interesting little feature here, and let me jump back here because I'd like to bring these over. I'm going to copy that and paste paste and copy that. There's a little interesting relationship going on here between the graph and the function itself. Oops, didn't want to do that. Okay. The solution set is all real numbers that are less than or equal to -10 or greater than or equal to 4. They were talking about this one here on letter B. If we want to write that in interval notation, here we're going to the left of -10. So we'd write parenthesis, -infinity, comma, -10. And then over here beyond 4, we would have 4 to infinity. And in between here, there's a little letter U. And it says the symbol U is called the union symbol. And it's used to denote the combining of two sets. The graph of the solution set is shown here. The one thing I really like on this, if we look at this graph, the two numbers that pop out, we got our absolute value bars isolated. In here, we have a 5, and here we have a 2. If you switch the sign here, this looks like a -5. If you change that to a positive, that is right in the middle of our solution set. And this is sort of like the radius of a circle. How far from that midpoint do we go? Well, we go 2 units this way to the endpoint at 7, and 2 units this way to the endpoint at 3. And that also holds true for letter B. Here, it looks like a +3, so swap the sign. That's a -3. That is exactly in the middle of our solution set. And 7 is how far we go from that to the left or right. From -3, we can go 7 units positive to 4, or 7 more units to the negative to -10. And what do we got here? Note that the graph of the inequality x minus 5 is less than 2, this here from part A, can be described as all real numbers within 2 units of 5, as shown here in the graph. Just an interesting little side note there. Okay, now for some practice. 4 of them. Real nice, easy one. Number 69, watch out for that 2. One of these is a no solution problem. And there's a couple ways sort of to pick up on it. And I'll show each of you, or I'll show you each of those ways as we're going over each of these problems. So pause the video, try these out, then start her back up, and see if you got the correct solutions. Okay, directions say, solve the inequality, sketch the solution on the number line. Some inequalities have no solution. The first one, nice easy one, slow pitch across the plate. Absolute value of x is less than 5. So we're going to jump the 5 over, make that a -5 is less than x, now the bars are gone, which is less than 5. So our number line, our graph, is going to go from 5 to -5. And here we know x is less than 5, no or equal to, so we have a parenthesis, and we're headed to the left. The other part says -5 is less than x, or x is greater than -5, so we're here going this way. There's our solution set. Now when you look at number 61, the first thing that really jumps out is we haven't seen anything like this. This number's negative. So first instinct of a lot of students is, well, it's going to jump over here, and over here it's going to switch signs to a positive 1. 1 is less than x minus 5, which is less than -1. Now right here, here's kind of a little a hint. If we ignore this x minus 5 in the middle, is 1 less than -1? No. You can see that in odd times pop up in other problems. So that's not the end all to say that this is no solution. If you keep going, and to solve for x in the middle, of course, we're going to add 5 all the way around. So this will be 6 is less than x is less than 4. If you try to graph it, we're going to have 4 and 6. X is less than 4. So that means I'm at 4 and I'm headed to the left. 6 is less than x, or x is greater than 6. Okay, now you might think, okay, we've seen graphs like that before. Nothing really weird is hopping out there. But if you go the extra mile and try to test some values, like if I plug in 5, if I plug 5 into the original inequality, in my bars, I'll get 5 minus 5, which is 0. Is 0 less than -1? No. So these are not solutions between 4 and 6, just as we would expect. But what if, say, I plug in 10? It looks like 10 would be in my solution set. But what happens? 10 minus 5 would be 5. Is 5 less than negative 1? No. So these are also not solutions. What if I come over here, less than 4, maybe 0? That's an easy number to plug in and test. If I plug in 0, 0 minus 5 is negative 5. The bars would make that positive 5. Is 5 less than negative 1? No. What's going on? Probably the easiest way to catch this as a no solution is back here to the original setup. Let x be a variable or an algebraic expression. Let a be a real number such that a is greater than or equal to 0. A must be positive. And that's not what we have here. That's a negative answer. So that sort of violates the setup to using this property of absolute values on inequalities. Another thing to look at, it's kind of a common sense thing, but it's real easy to skip by. Ignore what's in the bars. We have the absolute value of something is less than a negative number. We know that no matter what goes on in the bars will make that into a positive. Is a positive number ever less than a negative number? No, it just doesn't happen. So that is no solution. 61 is no solution. Number 65. Let's try this one out. Okay. Absolute value bars are alone, so that's good. I'm going to hop over and do my negative 9 on the left. Greater than or equal to 3 minus 4x greater than or equal to positive 9. And I want to get x alone in the middle, so I'm going to subtract out a 3. So now this is a negative 12 is greater than or equal to minus 4x greater than or equal to 6. One more step. We got to divide to get x alone. And we're going to divide by a negative. And you better know what to do when we divide by a negative. 12 and 4, both negative. They will divide out to be a positive, positive 3. These will cancel and we'll have x. And then 6 over 4, that doesn't divide evenly, but we can reduce the fraction to 3 halves. Positive divided by negative is negative. And don't forget, when you divide by a negative, the inequalities have now reversed. So now those are less than or equal to signs. Alrighty. Quick graph. We got, now here it's weird, usually a lot of times the negative number will be on the left, the positive number will be on the right. It doesn't matter, I can rewrite this. I'm going to put the negative 3 halves on the left, I'm going to put the 3 on the right, x in the middle, but just make sure your inequalities, your little alligators, are eating the same thing. Between the 3 and the x, the alligator is going to eat the x. So between the 3 and the x, the alligator's eating the x. Between the x and the 3 halves negative, the alligator's eating the negative 3 halves. So when we rewrote the inequality this way, we have reversed our inequalities yet again. It doesn't matter. You don't need to do that, when we graph it. When you graph it, though, of course, you want your negative number on the left. Negative 3 halves here, 3's here, 0 would be somewhere in between. So if you look at it this way, x is less than or equal to 3 halves. We're at 3 halves. We have a bracket. We're off to the left. 3 is less than x, or x is greater than 3. So we're going to be here with a bracket headed off to the right. And you could get the same thing from here. X is greater than 3 would be the first part. And then x is less than negative 3 halves, or negative 3 halves is greater than x, would still give us this. Just when you're doing your graph, if you get an answer like this, don't put 3 on the left and negative 3 halves here. That just doesn't make sense on a number line. Last one. Number 69 is a lot like the third example from the previous slide. In this one, remember we wanted to get the absolute value bars alone before we reflected that number to the other side and made it negative. Here we had to divide by 2. Not so here. Here we just want to add 2 to get those bars by themselves. So I'm going to add 2 to each of the sides here, and now I'll have my absolute value bars, 9 minus 2x inside. These are gone, so that's less than, and here negative 1 and 2 adds up to a positive 1. And now that we have our bars isolated, we can jump over here and write negative 1 is less than 9 minus 2x is less than positive 1. So we're getting x alone in the middle. We got a 9, and we got to subtract that 9 out of there. So negative 1 and negative 9 is negative 10, is less than. We still have a minus 2x in there. Don't lose track of that minus. Less than 1 minus 9 is negative 8. And now again, we're going to have to divide to get x alone, and we are again dividing by a negative number. So when we divide by the negative, of course, our inequalities are going to switch. Less thans become greater thans. The negatives cancel. 10 divided by 2 is 5. Those are gone. We have x. Negatives again cancel. 8 divided by 2 is 4. So just like the last one, we do have now the larger number is on the left. You know, just when you draw your number line, of course, don't put that number there. 4 and 5. 4 is to the left of 5. So x is greater than 4. We're here at 4, and we're headed this way. X is less than 5, so we're at 5, and we're headed toward the 4. There's our solution set. The numbers between 4 and 5 will make this true. Any number less than 4 or greater than 5 will make this into a false statement. And that's the end of 1.7. We'll do section 1.8 and then have a little test. The homework for this section is page 147, 46, 50 to 54 all, and 58 and 60. Watch out for no solutions.